Hello! Welcome to your instructional video on how to operate the Albatross UAV. First up, let's take a glance at weight and balance. You should avoid having the centre of mass further back than 0.16 metres when the aircraft is on the ground, as it will topple backwards. Please use the QR code to access the MATLAB tool, where you can input the weight values found on the nose, port and starboard gear, and it will calculate your centre of mass. It also includes other functions, such as being able to calculate the short period frequency and other uses. The link is provided in the description below. This graph here shows a plot of CM versus CL, and it indicates what the neutral point is. As you can see here, the aircraft is completely unstable, and in order to achieve static stability, we must decrease the centre of mass to around 0.13. You now may think that the aircraft is stable. However, we must also be stable in pitch. This means that when the aircraft pitches, it shouldn't roll uncontrollably. In order to achieve this, the centre of mass must be less than 0.058, aka the aerodynamic centre, aka a quarter chord. However, this is still quite close to the limit of stability, so it is recommended to add a safety factor. This depends on how manoeuvrable you would like the aircraft to be. You should put the centre of mass further forward if you are prioritising stability, and further back if you are prioritising manoeuvrability. When applying thrust, it is recommended to only use full throttle during manoeuvres. This is because the increase in static thrust as you increase the throttle decreases. To save battery, you can limit the throttle. The centre of mass should be around minus 0.018 in the y-axis. This is because a zero thrust pitch coupling moment is achieved. This indicates that when the thrust is applied, there is no change in pitch. This makes the aircraft easier to fly and an ability to apply a constant trim. Please also note that there is a torque produced by the propeller that must be counted with an input of roll. The nose gear does not provide sufficient input when taxiing. In order to taxi, it is necessary to travel at faster speeds to use the rudder. Unfortunately, this either results in a very large turning circle for low throttle, or a high chance of crashing for high throttle. It is recommended to avoid travelling over bumps and keep the speed low where possible, ensuring that minimal input is applied as to avoid wing strike or having the aircraft flip over itself. The control surfaces have a deflection of 15 degrees, positive and negative. The convention is that for pitching up that the deflection would be around 30 degrees, but please note that for this aircraft the deflection is only 15 degrees. The deflection is also symmetrical, both positive and negative, whereas the convention is that the pitch down deflection would be slightly less than that of the pitch up. Please note that on the simulation, the aircraft is sensitive to pitch, but the elevator input has no increments, so in real life it should be less pitchy. However, if you do find the aircraft to be too pitchy, you should move the centre of mass forward slightly. This can be seen in the graph shown. For lower airspeed and further aft centre of mass, the pitch response will be higher. The short period is much higher than in the predicted data. This could be due to a difference in test conditions. The centre of mass might be further aft in the test, or perhaps a different cruise condition was assumed. It could also be that a different amount of throttle was applied during the test. Just note that because there is a larger short period, this indicates that the aircraft has a less manoeuvrable and precise setup. The yaw short period frequency is negative and is larger in magnitude than the pitch short period frequency. This means that the aircraft is more sensitive to your inputs, so it's more likely to oscillate after an input has been made. So, roll rate, or shall we say sensitivity. This graph shows the roll rate as a function of aileron input. As you can see, for increasing speeds, the roll rate increases, which makes the aircraft more sensitive in roll for higher speeds. So be cautious of this if you choose to operate with a higher throttle or higher speed. Here is the drag polar graph. It shows that as the lift increases, the drag increases up until a certain point, at which the drag then decreases again as the lift increases. This indicates that we must perform past a certain lift point, otherwise the drag will be too high. Here is the lift curve, so from this graph we can get the max lift for each condition. As we increase the flap angle, CL max increases. This is due to the curvature of the aerofoil increasing the pressure differential. The angle of attack decreases more as lift is produced on the wings, producing a downward pitching moment. L over D versus CL. The lift-to-drag ratio maximum is 13.64, but the expected value is 30. This indicates that the manufacturer perhaps didn't account for tip losses, which cause more drag and less lift. Now we will have a look at the CM versus CL graph for different elevator angles. The elevator angle best for trim is shown to be around 5 degrees. This is because the line intersects with 0, 0, where there is zero lift and the pitching moment is also 0. Let's take a look at the long period frequency, or phugoid. As you can see here, it is actually only about 12 seconds of a long period. This is actually quite small, considering that a long period could be up to more than 30 seconds, so this is actually quite a good case. The minimum unstick speed is 15 meters per second. In comparison, the manufacturer suggested that the stall speed was 10.456 meters per second. However, this is not the case. This could be because of a miscalculation, as the manufacturer has assumed that the wings have more lift than they actually do. The cruise speed is around 20 meters per second. Make sure that you take this into account when you are bringing up the aircraft for takeoff. Varies because it varies due to the center of mass. An approximation can be made that it is around 3 degrees. However, it does vary with different values. As mentioned, the cruise speed is around 20 meters per second. Now, the minimum flight speed is 19 meters per second. And as you've noticed, this is quite near the cruise speed. So it's possible to suddenly experience instability, especially when performing a banked turn. So it's advised to increase the throttle for a banked turn and perhaps pitch up as well, because the aircraft does lose altitude while performing banked turns. The maximum trimmed steady level flight speed is 47 meters per second. This is 20 meters per second higher than the manufacturer's predicted value of 27.7 meters per second. This could be overestimated due to the uncertainties while experiencing the phugoid during high-speed flight. Thank you very much for listening to this video on how to operate your Albatross aircraft. If you have any more questions, don't hesitate to contact us and scan the QR code or visit the link in the description below.